So the last unit is chapters 9, 10, and 11. Chapter 9 deals with rational functions. So a rational function, just like a rational number, has a numerator and a denominator. A rational expression has a numerator and a denominator, but you're going to have at least a polynomial somewhere. It might be in the numerator, might be in the denominator, or it might be in both. So we're going to graph and analyze rational functions. We're going to use transformations, some of the same stuff that we have been working with, as well as use technology, and we'll examine the behavior of the graphs near their non-permissive values. So again, a rational function is written in the form f at x equals p at x over q at x, where p at x and q at x are polynomial expressions and the denominator q at x cannot equal 0. So some examples would be y equals 20 over x, or c at n equals 100 plus 2n all over n, or f at x equals 3x squared plus 4 over x minus 5. So there just has to be a variable somewhere. Both the top and the bottom do not have to be polynomials, but there has to be a variable somewhere. So the rational function that relates speed to time for a given distance is related to the base function y equals 1 over x by a vertical stretch. The graph of a rational function in the form y equals a over x represents a vertical stretch by a factor of a of the graph y equals 1 over x. Because y equals a over x can be written as y equals a times 1 over x. Graphs of rational functions of this form have two separate branches that approach asymptotes at x equals 0 and y equals 0. If you take the equation y equals a over x, the reason why you have asymptotes, well, the x asymptote comes from the fact that x can't equal 0 because you cannot divide by 0. Okay? The reason that y equals 0 is an asymptote is this. The fact that this equation, no matter what you put in for x, y will never equal 0. A rational function equals 0 when the top equals 0. And the top will never be 0. It'll always be something. Sometimes it's a constant, sometimes it's a polynomial. But it'll never be 0. So because the top can never be 0, the whole thing cannot be 0. And therefore y can never equal 0. So that will be the reason why y equals 0 is a horizontal asymptote for some of these functions. Okay, so when we look at the graph of y equals 1 over x, we'll graph it by using a table of values. We'll identify characteristics and talk about the behavior of the function for its non-permissive values. So we'll again do this by getting a table of values. Again, x cannot equal 0, that's a non-permissive value, but we can have both negative and positive values of x. So for example, I can start with some negative values of x. Maybe negative 1/4, negative 1/2, negative 1, negative 2, and let's do negative 4. When x is negative 1/4, 1 divided by negative 1/4, well, to divide by a fraction, we multiply by the reciprocal. That'll be the same as 1 times negative 4 over 1. 1 divided by negative 1/2 will be 1 times negative 2 over 1. 1 divided by negative 1 is negative 1. That'll be negative 1/2 and negative 1/4. So we see as x gets closer and closer to 0, the value of y will get smaller and smaller. It'll approach negative infinity. And as x gets larger and larger, the value of y will approach 0. Once again, the x-axis is an asymptote because you cannot have an x value of 0. In this case, the y-axis is an asymptote because y will never equal 0. The only way a rational function equals 0 is if the top equals 0. But the top is a constant, it's 1. So again, because of that, the x-axis, the line y equals 0, is a horizontal asymptote. So the first branch of this graph we'll get from our table of values that we just did. Once again, as x gets closer and closer to 0, the value of y gets smaller and smaller. It'll approach negative infinity. So as we come down here, as x gets closer and closer to 0, the graph approaches negative infinity. I've got some key points I can put on here: negative 1/4, negative 4, negative a half, negative 2, negative 1, negative 1, negative 2, negative a half, and negative 4, negative a quarter. So this is what this branch of the graph looks like. And again, as x gets smaller and smaller, the value of y will get closer and closer to 0, but it'll never get there. So that's that branch of the graph. To get the other branch, we will choose positive values of x. Maybe positive a quarter, positive a half, positive 1, positive 2, and positive 4. So 1 divided by a quarter will be 1 times 4 over 1. 1 divided by a half will be 1 times 2 over 1. 1 divided by 1, 1 divided by 2, 1 divided by 4. As x gets smaller and smaller, as x approaches 0, the values of y will get bigger and bigger. They will approach positive infinity. I do have some key points that I can plot, though. I've got the point 1 quarter comma 4. I've got the point 1 half comma 2. I've got the point 1 comma 1, 2 comma a half, 4 comma a quarter. This is what this arm of the graph looks like. So there's that branch of that graph. When we talk about some characteristics, we would talk about the asymptotes. So we'll have a vertical asymptote. The line x equals 0, and a horizontal one is the line y equals 0. Those are the asymptotes for this graph. Now, when we do the graph of y equals 6 over x, it's going to be the graph of y equals 1 over x with a vertical stretch about the x-axis by a factor of 6. So if we compared it to y equals 1 over x, y equals 6 over x will be vertically stretched about the x-axis by a factor of 6. That'll be the only difference. You will still have your asymptotes at x equals 0 and y equals 0. But if we compared all the y values on the previous tables, the new y values would all be multiplied by 6. Instead of going through 1 comma 1, these graphs will go through, or this graph will go through 1 comma 6. And instead of going through negative 1 comma negative 1, it'll go through negative 1 comma negative 6. All the y values are multiplied by 6. because that is our A value. So the graph might look something like that. There's that branch. And that branch. There's a vertical stretch about the x-axis by a factor of 6. It doesn't change our asymptotes. We're still at x equals 0 and y equals 0. And remember, these graphs always have arrows on the end because they continue forever in those directions. We can also do the domain and range of these graphs. Our domain would be all values of x such that x cannot equal 0, but all other real values are part of the domain. Our range would be all values of y such that y cannot equal 0. But all other real values are part of the range. So I did that one with set notation. Okay. So this next one still has an A value of 6, so it's going to be vertically stretched about the x-axis by 6 like the last one, but it's also going to be shifted, right? So this equation follows this format. Remember, the h is hooked directly onto the x with a plus or a minus. Whatever happens to the x also happens to the h. In this case, it's a denominator. So that 2 is an h value. And then the negative 3, and I should have used plus k there instead. The negative 3 is our k value. A k value of negative 3 means the graph is going to shift 3 units down. So if I talk about this as a transformation of y equals 1 over x, we have an a value of 6, which again means that we will have a vertical stretch about the x-axis by a factor of 6. We have a horizontal shift because h is positive 2. Remember, the value of h is always the opposite of what it appears to be. The general equation has x minus h in it. So our value of h is positive 2, which means it's going to shift 2 to the right. And then we have a k value of negative 3, which means it's going to shift 3 down. This means our asymptotes are going to shift. Our vertical asymptote will be at positive 2 because it shifted 2 to the right. And our horizontal asymptote will be at negative 3 because it shifted 3 down. So I'm just going to do a table of values in my head just to generate a couple key points for this graph. The first being when x is 3. When you let x equal 3 in this equation, the denominator, 3 minus 2, will be 1. 6 divided by 1 is 6, and 6 take away 3 is 3. So it's going to be the point 3, comma 3. You're signing out? That point right there. This graph will have an x-intercept, and we can find that by letting y equal 0. So let's do that. Our x-intercept is where y equals 0. So it'll be where 0 equals 6 over x minus 2 minus 3. So here you would add 3 to both sides. Next, we would multiply both sides by x minus 2. That'll get rid of the x minus 2 on the right. We can divide both sides by 3. So on the right side, when you divide 6 by 3, you'll get 2. And then when you add 2 to both sides, you'll get positive 4. Our x-intercept is at positive 4. So this gives us actually 2 points that we can use to help graph this branch of the graph. The other branch will be to the left side of the vertical asymptote. So we could let x equal 1. When x equals 1, the denominator, 1 minus 2, is negative 1. 6 over negative 1 is negative 6. Take away 3 is negative 9. So we have to kind of estimate where that is on our graph. Negative 4, negative 5, negative 6, 7, 8, 9, somewhere right there. We could find the y-intercept, because this graph does have a y-intercept, by letting x equal 0. So it'll be where y equals 6 over 0 minus 2, take away 3. 0 take away 2 is negative 2. 6 over negative 2 is negative 3. Minus 3 is negative 6. So the y-intercept will be at negative 6, which is about right there. So again, this gives us 2 points to help us sketch our graph, that branch. So there it is. Our domain. If I use interval notation, it's every value except positive 2, because that's where our vertical asymptote is. So it'll go from negative infinity to positive 2, and then again from positive 2 to positive infinity. Neither are included, so we have to use those rounded brackets. Our range, again, using interval notation, would go from negative infinity to negative 3, and then again from negative 3 to positive infinity. Again, rounded brackets are used because none of these values are included. Our asymptotes are at 2 and negative 3. If we did a mapping notation for this, the only thing that affected the x value was our shift to the right by 2 units. So x maps into x plus 2, but then y was multiplied by 6 because we had a vertical stretch by 6, and then decreased by 3 because it shifted down 3 units. So there's the mapping notation. Right? So on the next equation, again, this is a transformation of y equals 1 over x. We've got a value of a being 4, which again means we have a vertical stretch. About the x-axis. Then we have an h value of -1. Remember, the value of h is always the opposite of what it appears to be because the general form is x minus h. So that graph is going to shift one left. And a k value of +5. So it's going to shift 5 up. Because it's shifting 1 to the left, our vertical asymptote will go 1 to the left. It'll be at x equals -1. And it goes up 5, so that's where our horizontal asymptote will be at y equals +5. Once again, we could find a couple key points, one of them being the y-intercept. Our y-intercept is where x is 0. So it'll be where y equals 4 over 0 plus 1 plus 5. 0 plus 1 is 1. 4 divided by 1 is 4 plus 5 is 9. There's our y-intercept at +9. Let's find one other point here by letting x equal 1. When x is 1 on the bottom, 1 plus 1 is 2. 4 divided by 2 is 2, plus 5 is 7. So the point 1 comma 7 is also part of this graph. So that's that branch of the graph. The other branch is where our x-intercept will be. Our x-intercept is where y equals 0. So that'll be where 0 equals 4 over x plus 1 plus 5. Subtracting 5 from both sides, you'll get -5 on the left. If you multiply both sides by x plus 1, that'll get rid of the x plus 1 on the left. I would now divide both sides by -5 instead of multiplying out the brackets. You could, but don't have to. So that'll be -4/5, and then we'll subtract 1 from both sides. -4/5 is -0.8. Take away 1 is -1.8. There's our x-intercept at -1.8. Approximately there. Let's find one more point. Let's let x equal -5. And I chose that value because when x is -5, -5 plus 1 is -4. 4 divided by -4 is -1. And -1 plus 5 is 4. So -5, comma 4 is that point right there. Check that one more time. Oh, -5, comma 4. I had it in the wrong spot. That's better. -5 plus 1 is -4. 4 divided by -4 is -1. Plus 5 is +4. So this gives us a couple points for the other branch of that graph. Right? And remember, we always have arrows on the ends of our graphs. The domain of this, if I use set notation, all values of x such that x cannot equal -1, but it's all other real numbers belong to the domain. A range, all values of y such that y cannot equal +5. And it's all other real numbers. If we were asked to state the equations of our asymptotes, we'll have one at x equals -1, the other at y equals +5. And finally, if we wanted to state our mapping notation, X will map into x minus 1 because we're going 1 to the left. We're vertically stretching by a factor of 4, so y is multiplied by 4 and then increased by 5 because we're going up 5 units. Okay, I'll stop there for today. You can work on those 2 questions on page 442. I will post those solutions to Google Classroom so that you can check your answers. Don't forget that review from the last unit has to be handed in. Some of you did already, but a lot haven't, so make sure you get that done and handed in, okay?